let us start with the self-inductance concept. Let us say this is coil, and this coil inductance is L, and current I started flowing through the coil, then flux is developed. Due to the change in this flux, the flux linking with the coil is changing, then according to Faraday law, EMF gets induced. So now what is the meaning of this self-inductance? And here you see the voltage produced in the coil due to the change in the flux in the coil, and that change in the flux is due to the current flowing through the same coil. So due to the current flowing through the same coil, we are getting the EMF. That is known as what? Self-inductance. The voltage produced in the coil due to the change in the magnetic flux surrounded by the coil, essentially due to the same coil current itself. So this is known as what? Self-inductance. Or we can also define as it is a property of the coil due to which it opposes the change of current flowing through itself, is called as self-inductance or inductance of the coil. So we denote with what? L. Now let us start with the mutual inductance, and mutual inductance we denote with M. Here time varying magnetic flux which is produced by the changing current in one coil may also cause voltage in the other coil also. So let us say this is the one coil and this is the other coil. So current started flowing here and flux is developed here, and let us say this flux is developed, this flux is links with the second coil, and here I am getting the EMF in the second coil due to the change in the flux in the first coil. That EMF is nothing but what? Mutual inductance. The property of the coil due to it opposes the change in the current in the other coil is known as what? Mutual inductance. The property of one coil due to which it opposes the change in the current in the other coil, this is known as what? Mutual inductance. Let us say this is coil A and this is coil B, and current is flowing through the coil A is I1. Flux is linking with both the coil, we are assuming as pi 1 2. So EMF induced in the coil is proportional to current flowing through the coil, that is change in the current flowing through the coil di1 by dt. So E is equal to M into di1 by dt. This M is known as what? Mutual inductance. Now here we will see one important coefficient, that is coefficient of coupling K. Let us say there are two coils, this is coil 1 or coil A, and there is one more coil, this is coil B. The flux developed in the coil 1, let us say it is pi. If it is entirely linking with coil B, the same flux is linked with the coil B, then we say maximum coupling is happening. That is, we say coefficient of coupling is equal to 100%. 100% is nothing but what? 1. The coefficient of coupling between two coils is defined as the fraction or whole of the magnetic flux produced by the current in the one coil that links with the other coil. It is denoted by K. So K is equal to 1 or 100% means flux developed in the first coil is entirely linking with the second coil. Let us say flux developed in the first coil, only 50% of it is linking with the second coil, then we say coefficient of coupling is equal to 50%, or we can say coefficient of coupling is equal to 1 by 2. Suppose two coils are having self-inductances L1 and L2, then what is a mutual inductance formula? M is equal to K root L1 L2. This is very important formula. This K nothing but coefficient of coupling. So K value may be 1 or half based on how much fraction of the flux is linking with the second coil. So very important formula, M is equal to mutual inductance, M is equal to K into root L1 L2. L1 L2 are self inductances of coil 1 and coil 2. M is the mutual inductance between coil 1 and coil 2. Now let us start with the inductors in series. Now here I have not taken any mutual, let us say here coil L1 and coil L2. So if L1 and L2 are connected in series, without any mutual inductance, there is no mutual inductance, then total equivalent inductance formula is L1 plus L2. Like R1 plus R2, here also L1 plus L2. But here there is mutual inductance M present between coil 1 and coil 2. Here mutual inductance M is there between coil 1 and coil 2. So flux developed in the coil 1 is pi 1. Flux developed in the coil 1 is pi 1. Flux developed in the coil 2 is pi 2. And here you see some dots you will see here. So this is a dot convention. This dot convention denotes how the direction of the current in both the coils. You see here, or how whether the flux developed by both the coils are both are in the same direction or opposite direction. This will be indicating with the help of dot convention. You see in coil 1 current is entering into the dot. In coil 2 is also current is entering into the dot. Then we say series aiding. That means flux developed by the coil 2 and coil 1 both are in the same direction. They gets added pi 1 plus pi 2. In both the coils current is entering into the dot. Both the coils current is entering into dot. Entering into dots. So then we say both the flux gets added. So that is called series aiding. Aiding means supporting each other. Then we see what is a mutual inductance formula. Total inductance formula. When L1 L2 are connected in series and M is a mutual inductance and both are connected in series aiding, total equivalent inductance is equal to L1 plus L2 plus 2M. The formula is L1 plus L2 plus 2M. Let us say if mutual inductance is not there, means M is equal to 0, then we get the formula L equivalent is equal to L1 plus L2. Now we will see inductors L1 and L2 both are in series with the mutual inductance M, but series opposing condition. You see current is entering into the dot in L1, but current is leaving from the dot in L2. In one inductor current is entering into the dot, in one other inductor current is leaving from the dot. Then both the flux are in the opposite direction. So both the flux developed by the L1 and flux developed by the L2, both the flux opposes each other. So total flux is nothing but difference of the two fluxes. That is called opposing condition. Then mutual inductance will be negative. Then we will get the formula L1 plus L2 minus 2M. L equivalent total inductance equal to L1 plus L2 minus 2M. Now let us see when inductors are in parallel. So L1 and this is L2 and this is L3, both are in parallel, and here dot convention is given, and in L1 current is entering into the dot, in L2 current is entering into the dot, in L3 also current is entering into the dot. Then usually without mutual inductance, total inductance formula is 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3. And mutual inductance between any pair of coils, let us say between L1 and L2 or L2 and L3 or L1 and L3, it may become positive or negative based on the dot convention. Dot notation in one coil gives the information. See how we will calculate the equivalent inductance here is, say L1 without mutual inductance, L1 nu with the mutual inductance. So L1 nu is equal to self inductance L1 and M12 is there. M12 is nothing but between L1 and L2 mutual inductance is M12. So in L1 current is entering into the dot, in L2 also current is entering into the dot. So M12 is positive. So M13 in L1 current is entering into the dot, in L3 also current is entering into the dot. So M13 is also positive. So L1 plus M12 plus M13, this is the new L1 value. In place of this L1 we will substitute this L1 new. See here, L1 and L2 L2 L3 are connected in parallel, and we are finding out the equivalent inductance. So equivalent inductance formula, 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3. This is the formula. So for series connection, L1 plus L2 plus L3. For series connection, L1 plus L2 plus L3. And for parallel connection, 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3. Now let us start with the capacitors in series. So when capacitors are connected in series, what is the total capacitance formula? So now you see here, capacitors are connected in series, C1, C2 and C3 all are connected in series. Then what is the total capacitance formula is 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. In resistors and inductors, when the things are connected in series, we will get the R1 plus R2 plus R3 or L1 plus L2 plus L3. But in capacitors, it is the opposite formula. So when the capacitors are connected in series, 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now when capacitors are connected in parallel, C1 and C2, C3, all the three are connected in parallel across the power supply voltage V, then total capacitance C is equal to C1 plus C2 plus C3. This is the formula. Capacitor series formula is same as resistors inductors parallel formula. Capacitor parallel formula is same as resistors inductors series formula. Now here we will discuss about one important concept called open circuit. Let us say here one load is connected now. Here one load is connected. But after some time I have disconnected the load. This is open circuit. This is nothing but what? Open circuit. As power supply is there, but as the closed circuit is not formed, there will not be any current flowing through the circuit. Therefore, in open circuit, current will not be there. In open circuit, current will be what? Zero. So, but impedance is what? Infinite. In open circuit, current is zero. But voltage means here you see, as no current flows through the resistor, voltage drop will be zero in the resistor. So whatever the input supply voltage is there, the total voltage will be appearing at the whatever the input supply voltage, total voltage will appear at the this open circuit terminals. This voltage would be what? V. So in open circuit current is zero. Voltage, it depends upon the circuit, and impedance of the open circuit is what? Infinite. So as the impedance or resistance is infinite, the current is what? Zero. Current is zero, resistance is infinite, voltage depends upon the circuit. And now let us see what is a short circuit. See, this resistor is shorted with one coil. So as the resistor is shorted, whatever the current coming here, no current flows through this resistor. Entire current will be flowing through this short circuit only. Because short circuit resistance is what? Zero. So entire current will be flowing through short circuit. No current flows through this resistor. This resistor becomes dummy now. So in short circuit, current will be large, resistance is equal to 0, and voltage is also 0. Voltage across short circuit is also 0. As resistance 0, voltage will be 0. Next, we'll discuss about basics of electromagnetism or basics of electrical machines. So in DC generator or in DC motor, transformer, alternator, three-phase induction motor, in all these concepts, some fundamental concepts are very useful that I am going to discuss here. So first let us start with very basic concept, that is nothing but what? Flux. So this is the magnet, north pole and south pole. You see, the flux is flowing from north pole to south pole. The flux is starting from north pole and coming to the south pole. So outside the magnet it is flowing from north pole to south pole. Inside the magnet it is flowing from south pole to north pole. So total number of lines of force in a magnetic field is known as what? Flux. So total flux lines is known as was flux. It is denoted with pi, and the unit of flux is Weber. 1 Weber means how many lines of force? 10 power 8 lines of force is known as what? 1 Weber of flux. Direction of the flux we denote as north pole to south pole. Next, what is the meaning of flux density? What is the meaning of flux density? Flux density is equal to flux per unit cross sectional area. So flux density B is equal to, what is the formula? Flux by area. So Weber per meter square is the flux density formula. Now the magnetic flux direction we can find out using right hand ruler. It is also known as thumb rule. So whenever current flows through any coil, the flux is going to be developed across that particular coil. The magnetic field is going to be developed. This magnetic field direction we will find based on the current direction. How we can find means using right hand rule. First, let us say here I am taking two conditions. Let us say this is surface, and into the surface, when the current is flowing into the surface, what is the flux direction? Here we will take two things. One is current is flowing into the plane, then what will be the flux direction? Current is going out of the plane, what is the current direction? So what is right hand thumb rule is, you hold the current carrying conductor with the right hand in such a manner that your thumb represents the current direction, your thumb is representing the current direction, then your curling fingers will represent the flux direction. Your curling fingers represents the flux direction. So whenever current is flowing into the plane, flux direction will be in the clockwise direction. So flux direction will be clockwise. Whenever current is flowing out of the plane, whenever the current is flowing out of the plane, then flux direction, our curling fingers will be representing the anti-clockwise direction. You see, current is going into the plane. These curling fingers are representing flux direction. That flux is nothing but in which direction? Clockwise direction. Whenever current is going out of the plane, then our curling fingers will represent the flux direction, that is in the anti-clockwise direction. In this diagram I am showing the right hand thumb rule. So this thumb we have to keep in the current direction, then these curling fingers will be representing the flux direction. You see curling fingers, so flux direction will be like this. You see current is going out of the plane. When current is going out of the plane, so we kept the thumb in the current direction, then the flux direction will be like this. This is anti-clockwise direction. So current is going into the plane, then I kept the thumb in the current direction, then flux will be like this. So the flux will be like this. So this is the clockwise direction. Now let us discuss some few important terms related to this flux magnetic field, magnetic circuits. Permeability mu. Permeability means it is the ability of the material to conduct the magnetic flux. So more permeability means more it can conduct the more flux. So there is a one formula, mu is equal to mu naught into mu r. Mu naught nothing but free space absolute permeability, that is mu naught is 4 pi into 10 power minus 7 Henry per meter. So relative permeability mu r is nothing but it is defined as ratio between mu and mu naught. So then we will get the formula mu is equal to mu naught into mu r. Next, field intensity or magnetic force. Field intensity at any point in a magnetic field is the force acting on a unit north pole. So this field intensity is nothing but mmf divided by mean length, average length. So Ni divided by L. So magnetic force H is equal to Ni divided by L. And we have one formula between flux density and magnetic field intensity. B is equal to mu H, but we know mu is nothing but what, mu naught into mu R. Next, arrested statement. So what arrested statement or magnetic effect of current is, when current flows through any coil, the flux is going to be developed. The flux is going to be developed. More current flows through the coil, more flux will be developed. Less current flows through the coil, less flux will be developed. And whatever the flux developed, that flux direction is, the direction of the magnetic field is perpendicular to the direction of the flow of current. This direction of the magnetic field is reversed, then direction of the flux is also going to be reversed. Next we will start with the Fleming left hand rule. So what is the Fleming left hand rule? Before going to Fleming left hand rule, so whenever current carrying conductor is placed in a magnetic field, whenever, let us say this is north pole and it is south pole, whenever current carrying conductor is placed in a magnetic field, whenever current carrying conductor is placed in a magnetic field, let us say one conductor is placed, then force is going to exert on the conductor. Whenever current carrying conductor will be placed in a magnetic field, force is going to exert on that conductor. So based on the, we want to find out the this force exerted on the conductor direction. So that will be determined using the Fleming left hand rule. So Fleming left hand rule means, stretch out your left hand thumb, forefinger and middle finger in such a manner that all the three fingers are perpendicular to each other. Then you keep your forefinger in the magnetic field direction. You keep your middle finger in the current direction. So then this thumb is going to represent the force on the conductor direction. So I know the magnetic field direction. In that direction I am keeping the forefinger. I know the current flowing through the conductor direction. In that current direction I am keeping the middle finger direction. Then our thumb is going to represent the force on the current carrying conductor. So this is Fleming left hand rule. Now some basic terms here. MMF will cause the flux. MMF is like EMF in the electric circuit. So magnetomotive force is the force which drives or tends to drive the magnetic flux through the magnetic circuit. So MMF is equal to number of turns into current, and unit is nothing but what, ampere turn. So more MMF, more flux gets developed. Less MMF, less flux gets developed. Reluctance is like a resistance. It opposes the development of the flux. Resistance opposes the flow of current. Reluctance is going to oppose the flux. Reluctance is the property of the substance which opposes the flow of magnetic flux. And permeance, like permeability I told you, it is a measure of the ease with which the magnetic flux lines can be established. That means permeance is more means the flux gets developed very easily. Permeance is more means reluctance is less. So permeance is less means reluctance is more. It is permeance shows how the flux will be developed. And what is a magnetic leakage or leakage of flux? So the flux which is not flowing in the desired direction, that is nothing but what, leakage flux. The magnetic flux that does not follows the desired path is known as what, leakage flux. And now let us see very important table, the similarities and dissimilarities between magnetic circuit and electric circuit. In magnetic circuit, flux will be there. In electric circuit, similar thing is nothing but what, current. Flux density B is equal to flux by area, and current density is equal to current by area. And MMF, ampere turn, and this MMF will produce the flux, will cause the flux. EMF, volts is a unit, it will cause the current. And reluctance, which opposes a flux, and resistance will oppose the current. Ohm's law is flux is equal to MMF by reluctance. Ohm's law is current is equal to voltage by resistance. Permeance nothing but it is a reciprocal of reluctance, and conductance is reciprocal of resistance. permeability mu is equal to 1 by reluctance, and conductivity sigma is equal to 1 by resistance. Next, reactivity is nothing but what here resistivity. MMF drop is pi into S and voltage drop is I into R. Magnetic field intensity Ni by L, and electric field intensity V by D, and magnetic field intensity Ni divided by L. Now we'll see what are the dissimilarities between magnetic circuit and electric circuit. Magnetic flux does not flow, it is an imaginary thing, but electric current will flow is in one circuit. There is no magnetic insulator. For example, flux can be set up even with the air also with more mmf. There is no magnetic insulator, but all the substances cannot allow the flow of current. We have insulators, electric insulators. We have air is an insulator. And here magnetic circuit stores the energy in the magnetic field. Electric circuit, flow of current in electric circuit involves a continuous expenditure of energy. Here it stores the energy, it consumes, and here energy gets wasted. The reluctance of a magnetic circuit is not constant, it depends upon the B. The value of the resistivity vary slightly with the temperature. The resistance of the electric circuit practically constant. Circuit resistance always constant, but here reluctance of the circuit is going to change, and it depends upon the flux density. Now here we'll discuss very important concepts which are useful in our electrical machines, that is Faraday laws of electromagnetic induction, Faraday first law and Faraday second law. This Faraday first law will tell us how the EMF is induced in the circuit, how the voltage is induced in a coil. So according to Faraday first law, whenever we have a conductor and whenever we have a flux, either conductor is rotating or flux is rotating, or flux linking with the coil is changing, then EMF will be induced. So according to Faraday first law, whenever conductor cuts the magnetic flux, EMF will be induced, or whenever flux linking with the coil is changing also, EMF will be induced. So to get the EMF, what we require conductor, we require flux, and flux linking with the conductor must be changing. So flux linking with the conductor has to change, means either conductor has to rotate or flux has to rotate. If conductor and flux both are not rotating, both are stationary, then flux linking with the conductor must be AC flux, then only EMF will be induced. So this is Faraday first law. Faraday first law will tell us how the voltage or how the EMF is induced in a coil. And Faraday second law will tell us what is the magnitude of the induced EMF. The magnitude of the induced EMF depends upon the rate of change of flux linkage. So E is equal to ND pi by dt. This minus ND pi by dt, this minus represents, this here minus represents EMF is induced in such a manner that it opposes the very cause of it. So E is equal to minus ND pi by dt. N nothing but number of turns, and E nothing but EMF, d pi by dt nothing but rate of change of flux linkage. So this is Faraday first law and Faraday second law. And right hand screw rule, let us see the right hand screw rule. It also like right hand thumb rule. It states that hold the cork screw in your right hand and you rotate in such a manner that it advances in the direction of the flow of current. You rotate the screw in such a manner that it is rotating in the current direction. Then the direction of the rotation of the screw will give us the direction of the magnetic lines of force. So based on the current, the flux direction will be there. To determine the flux direction, we can use the right hand cork screw rule. Now let us see force on a current carrying conductor. As already we have discussed, whenever current carrying conductor is placed in a magnetic field, force is going to exert on the conductor. See here, this is a north pole and this is a south pole, and this is a flux direction, let us see. And here this is a conductor, and on the conductor this is a flux direction. So on the top of the conductor, main field flux and the flux developed by the conductor both are in the same direction, left to right. So these both flux gets added, pi 1 plus pi 2. Let us say pi 1 is the main field flux that is flowing from north pole to south pole. Pi 2 nothing but this conductor is there na, it is developing some flux, and on the bottom main field flux is from left to right, that is like this, and conductor flux is from right to left. So both flux get subtracted. On the top of the conductor magnetic field is strengthening, on the bottom of the conductor magnetic field is weakening. Because of this unequal distribution of the flux, the force is going to exert on the conductor. So you see, on the top of the conductor main field flux is from north pole to south pole like this, and this conductor flux is also same direction, north pole to south pole. Both flux gets added, main field flux developed by the conductor, and on the top, on the bottom of the conductor, you see on the bottom of the conductor, flux, main field flux is again from north pole to south pole, you see. But flux developed by the conductor is from south pole to north pole, so both flux are in the opposite direction, they get subtracted, so total flux is what, decreasing. The magnitude of the force on the conductor F is equal to BIL. What is the force acting on the conductor? That force is equal to BL. Flux intensity B, I is the current flowing through the conductor, L is the length of the conductor. So BL sin theta, but theta value is 90, so sin 90 is nothing but what, 1. So what is the basic requirement to get a EMF? We need a conductor or coil, we need a flux, and there should be some speed difference, relative speed between conductor and flux. So whenever we have some speed difference between conductor and flux, then only we will be getting the EMF. Whenever we have the relative speed between conductor and flux, then we will get the EMF. Or the flux linking with the conductor must be changing. If I take DC generator, in DC generator, the conductor is placed on the armature, so conductor is rotating and flux is placed on the stator. Flux will be stationary. Means flux speed is equal to what? 0. So relative speed is speed difference. Let us say conductor is rotating at n speed, flux is rotating at 0 speed. Relative speed is equal to n minus 0. We have some relative speed, so EMF is induced in the conductor. So this is about the DC generator. In three-phase induction motor also, we will be having some relative speed. So ns minus n. So ns is a flux speed, n is a conductor speed. And now, in case of transformer, there is no relative speed, but flux linking with the conductor is a AC flux, so then we'll be getting the EMF. We have two types of EMFs, that is dynamically induced EMF and other one is statically induced EMF. Let us see. So as already we have discussed, EMF induced in a conductor is, what is the formula? BLV sin theta. EMF induced in a conductor, that is BLV sin theta. Statically induced EMF means conductor and flux both are stationary. So conductor and flux both are stationary, but flux linking with the conductor is a AC flux, alternating flux, or flux linking with the conductor is changing. Then we'll get the EMF. That EMF is known as what? Statically induced EMF. Flux is not rotating, conductor is also not rotating. Dynamically induced EMF means conductor is rotating and flux is stationary, or flux is rotating and conductor is stationary. Then we'll get the EMF. That EMF is nothing but E is equal to BLV sin theta, and this V nothing but velocity at which the conductor is rotating. EMF induced direction in a conductor or coil we determine with the help of Fleming right hand rule. So three things are there. One is flux direction and another one is conductor rotation direction, conductor motion direction, and the other one is EMF. So if I know the flux direction, magnetic field direction, if I know in which direction the conductor is rotating, then I can determine the EMF induced direction. So this is Fleming right hand rule. Stretch out your right hand thumb, forefinger, middle finger in such a manner that all the three fingers are perpendicular to each other. Then you keep your thumb in the, you keep your, you keep your thumb in the conductor rotation direction. You keep your forefinger in the magnetic field direction. Then your middle finger will represent the EMF induced direction. So this is Fleming right hand rule with which we can determine the EMF induced direction. Next, Lenz law. With Lenz law, we can determine the EMF induced or EMF current direction. This law is useful to know the direction of the induced EMF in some cases, or hence current direction. What is the statement of Lenz law is EMF induced in a coil which opposes the very cause of it. Lenz law states that an induced current or induced EMF due to induced EMF will flow in such a direction that it opposes the very cause of it. Induced current will flow in such a manner that it opposes the very cause of it. An induced current always flows in such a direction that the field opposes any changes in the existing field. Here we will see DC generator. It works on the principle of electromagnetic induction. So it converts mechanical energy into electrical energy. And DC motor, it converts electrical energy input into rotation, that is mechanical energy rotation output. And DC motor works on what principle? When current carrying conductor is placed in a magnetic field and the force is going to exert on the conductor. DC generator on the electromagnetic induction, DC motor on whenever current carrying conductor is placed in a magnetic field, the force is going to exert on the conductor. So here the force is nothing but what? Torque. So we need to have a force or we need to have a torque means we need two magnetic fields. In DC motor we will be having armature winding, we will be having field winding. So armature winding produces armature flux, field winding produces field flux. Because of these two fluxes we will get the force or torque. Next, transformer. So in a transformer will not convert one form of energy into other form of energy, but it increases the voltage level or decreases the voltage level. It transfers the electrical energy from one circuit to the other circuit. It works on the principle of mutual induction. And next device, that is three-phase induction motor. It converts electrical power into mechanical energy, and it works on the principle of again mutual induction, and current carrying conductor is placed in a magnetic field, then force is going to exert on the conductor. Here electrical machines are classified into two types, that is DC machine and AC machine. And again DC machine we have DC generator and DC motor. In AC machine we have AC generator or synchronous generator, also called as alternator. And in AC motor we have synchronous motors and induction motor. In induction motor we have single phase induction motor, we have three phase induction motor, and one more AC machine, that is nothing but for transformer. So these are the basics of electrical machines or basics of electromagnetic induction. What exactly we have discussed in this lecture is, quickly I'll give a glance here. First we have discussed how the flux will be developed. Then we discussed how the EMF will be induced. So to get a EMF we need conductor and we need flux and we need relative speed between conductor and flux. And how to determine the EMF direction and how to determine the flux direction. We have discussed about Fleming right hand rule. We have discussed about Fleming left hand rule. And we have discussed about the types of EMFs, statically induced EMF and dynamically induced EMF. and we have discussed about how the force or how the torque is developed on a conductor. Whenever current carrying conductor is placed in a magnetic field, then force is going to exert on the conductor. And we have discussed about like some mmf and reluctance, some terms related to the magnetic circuits. Thank you. In the next video we'll discuss problems on series resistance and parallel resistance, and we discuss problems on this basic electromagnetic induction. Thank you.